Hello, in this video we will talk about t-distribution. And t-distribution, also formally called student's t-distribution. And this is very similar as normal distribution, which is most commonly used in statistics. And the situation is that when we use t-distribution, if the sample is small sample, usually no more than 30, and both t and normal distribution are often used for hypothesis testing for the population mean. So population mean. So if we want to test a hypothesis about population mean, when we have enough sample size, several hundred, for example, and if the population is not very far away from normal, then we can use normal distribution from the sample mean to do hypothesis testing for the population mean. But if the sample size is less than 30 and we do not know the standard deviation of the population, then we can use t-distribution because we want to use the standard error from the sample in t-statistics. So, for example, if we look at this figure, this is the t-distribution's density curve, and it is very close to normal, but depends on the degrees of freedom. So if the t-distribution has a very high degrees of freedom, then it will be very close to the standard and normal distribution. And usually t-distribution has a thick tail than the normal distribution. So if we want to test the population mean and we get a sample mean, for example, we have 20 sample size and get the mean x bar, then we will test the population mu if equal to, for example, 40. Then we use this sample mean minus the population which we want to do hypothesis testing, then divided by s times square n. So here n is the sample size, 20 here. And S is the standard error or standard deviation from the sample. Because we do not know the population standard deviation or variance, so we use the sample information. So here you can see only this one is the value we want to do hypothesis testing and all the other from the sample. So we have enough information, get this T called test statistic or t-score. Then this is the one way for the hypothesis testing. If we get this t-score is very large, if we look at this figure. For example, usually we take 2, around 2 is a critical value for the t. So if we get a t larger than, for example, 2 or very significantly larger than 2, so we usually will reject the hypothesis of this population equals this value, right? So because if the population equals this value, then this statistic will follow the t-distribution with these degrees of freedom. Then the value of t larger than 2, for example here, will return a very, very small p-value. A p-value is mean the probability on the right side of this critical value. So this is a small probability event which occurs. So we have confidence level which equals 1 minus this p level. For example, we have 97% confidence to say that the population mean equals this value will be rejected or not equal to this value. But on the other way, if we do not use this, do not calculate statistic use this way, we just we just use a critical or presume the critical value, for example, t equals 2. Here, then we use the same information from the sample, then we can calculate a confidence interval of the population mean. So from this way, if the confidence interval cover this mu value, so we can also do not reject this hypothesis testing. So if the confidence interval does not cover this mean value, then we will reject the hypothesis that the population equals this mean value, right? So this is the two way around. And here we take a look at an example. So suppose a researcher wants to estimate the average daily study time of students before exam. So we get a random sample of 20 students and report an average X bar of 4 hours and sample standard deviation 1.5 hour. Then we want to construct a 90% confidence interval for the true population mean. So it's quite simple that we just fill these numbers into confidence interval formula in the previous page. So we have X bar equals 4 and S equals 1.5 and N equals 20. And because we want to get 90% confidence interval, then we have degrees of freedom 19, and we check the t distribution table for critical value for the 5% on the right side and with 90 degrees of freedom. So we get this value is 1.729. So if we look at this page, so here we get about here 1.729 here because we set a 90% confidence interval, so which means the central part of this curve will have 90% probability. So this value is about here 1.7 here because 5% on this side and 5% on other side. So this value is 1.7. Then we fill in all these values in the confidence intervals formula, and we'll get this 90% confidence interval for the population mean is about between 3.42 and 4.58. So what mean this value tell us? So if we want to make hypothesis testing of the population mean equals 4 or not, 4 hours, then this value covers 4, right? Or if we want to test a 4.5, for example. So this value covers 4.5. So we have 90% confidence to say that the population mean is not significantly different from 4.5. And on the otherwise, if we want to test, for example, population mean equals 5 or not, but from this sample, all the information from the sample and from this presumed t-critical value, then we get this confidence interval does not cover 5. So we have 90% confidence to say that the population mean does not equal to 5, right? Thanks for watching for our statistics video, and we have also a website for Python and R tuning and a lot of examples including Python and R programming and statistic data analysis. Thanks for watching.